Hello everyone, my name is Subarnarekha Biswas and today I'll be presenting on strain measurement, an essential aspect of structural geology and deformation analysis. Let's begin with an introduction to why strain measurement is important. Strain represents the deformation of rocks in response to stress. It helps us interpret tectonic processes and stress regimes. Strain can be retrieved from rocks through a range of different methods, and it can be quantified using usually two types of measurement: longitudinal strain and angular strain. Longitudinal strain is the change in length of lines, whereas the angular strain corresponds to the change in angles in between lines due to rotation. Hence, the parameters used to measure strains are elongation, denoted by E, stretching, denoted by S, and quadratic extension, denoted by lambda for the longitudinal strain, and shear strain for the angular shear. Now, longitudinal strain analysis can be carried out in 1D as well as 2D. I will be explaining how to get the idea of the strain in 1D and 2D both. Coming to the longitudinal strain in one direction. Strain marker is a very important factor here. Strain markers are the features that preserve information about deformation. There can be structures like wooden edge dikes or layers, or minerals or linear fossils such as belemnites or any other originally known shapes. These are all the natural structures found in rock which indicates a change in length. So, identifying and interpreting these markers is the first step in strain analysis. Here we see, let me make it the pointer, yeah. So here we see two elongated belemnite fossils found in Jurassic limestone from the Swiss Alps. As we can see, the two belemnites have been stretched in different ways, which gives us some idea about the two-dimensional information also about the strain field. As you can see, the upper belemnite has experienced sinister shear strain, and the lower one here has experienced maximum stretching direction. So, to get an idea about the extension, what we can do is, first we can get the final length from this, and then maintaining the scale, definitely we can get the sum of all these parts present here to get the initial length. So after getting these two values, what you can do is subtract the initial length from the final length, and dividing it by the initial length, we get a value which indicates how much extension these fossils have gone through, to give you an idea about the strain condition of the rock. Longitudinal strain in 2 dimension. When 2-dimensional markers are available, like oolites, as we can see in this first diagram, these are fossils of oolites, and next we also have reduction spots, as you can see here. We can analyze strain in 2D from these sections. Next we have angular strain. Angular shear is the changes in the angles from the initial state. It is measured when the original angular relation between two lines is known. This is used to find the shear strain from this formula, which is the tangent of angular shear. Now, there are several strain markers such as trilobite, brachiopods, which have two originally orthogonal lines of symmetry. As seen here, this is a fossil of the deformed trilobite, where this used to be the two orthogonal original lines of symmetry, which after deformation is shown like this. Hence, this is the angular shear. this rock body has experienced, from which we can get the shear strength. So next is the Wellman method. The Wellman method is a geometric approach for determining strain in 2D, meaning it gives strain in 2 dimensions in a section. It is applied mainly to fossils that originally had orthogonal symmetry. From this method, we can get the strain ellipse by drawing parallelograms based on the orientation of regionally orthogonal pair of lines. So how to do it? Let's take a look at how this is done. So this is multiple brachiopods fossils. The hinge line here, the hinge line and the symmetry line are marked. These two are used as a pair of lines that were orthogonal in the unstrained state. Now, what is done is a line of reference is chosen. It can have any arbitrary orientation. Now, this reference line must have two defined endpoints such as A and B. A pair of lines is then drawn parallel to both the hinge line and the symmetry line for each fossil so that they intersect at the endpoints of this reference line. So from like this we can get the orientation of this hinge line with respect to the reference line and of symmetry line and plot it in a way so that it forms such geometric figures. Now, if the rock is unstrained, this geometric figure will define rectangles. But if there is a strain involved, they will define parallelogram. As we can see for this fossils level 6, this is a parallelogram, and also fossils level 4 and many. Now to find the strain ellipse, simply what you need to do is fit an ellipse to the numbered corner of the parallelogram like this. So after joining this we can get a strain ellipse. Now from this strain ellipse we can get the ratio of the strain from the actual ratio of the strain ellipse. So next we have another important method, which is another graphical approach for estimating finite strain from deformed elliptical objects. This method assumes an initially random distribution of ellipse long axis orientation and a range of initial long to short axial ratios, that is Ri. So before going into how this method works, let's give you an idea about what are the important parameters of it. So we have first Ri, that is the initial axial ratio of any arbitrary elliptical object. Rf is the finite axial ratio of any arbitrary elliptical objects, and the Rs is the axial ratio of the strain ellipse. Rf max is the maximum final axial ratio, whereas the Rf mean is the minimum final axial ratio. So now, it is also assumed that the ellipses have the same ellipticity before the deformation starts. Because the new shapes are different and depends on the initial orientation of the elliptical markers. So here is the strain markers of random distribution of its long axis orientation, as we can see in the diagrams. And 2 increments of pure shear is applied to this series of ellipses with different orientation. Firstly, in this diagram, Rs is the added pure shear, which is of 1.5, and in the next phase, it is of 3. From this consecutive application of the pure shear, we see that the markers have deformed and finally has reached this state. All the ellipses have the same initial shape, that is r equals to 2, and they plot along a vertical line. As we can see here that the spectrum of RF values is plotted against that orientation in the y-axis, and more specifically against the angle between the long axis of the ellipse and a reference line. So now, after the pebbles are traced, the RFI plot can be used to find the values of the RF max and RF minimum. Once these values are obtained, it is very straightforward to calculate the ratio of the strain ellipse, that is RS, and the maximum initial electricity, that is Imax. Using these two equations for two different cases, we can get the idea about the stress condition here. As you can see, initially it has the same Ri, so plotted like this. The Ri value was 2. After application of one phase of pure shear, it all deformed differently, and giving this Ra values like this, we can get the maximum Rf values and the minimum Rf values. And now finally we have this curve. So from choosing this equation, we can get the proper quantification of the strain ratio. So next is another method, which is the Fry method. This method assumes that circular objects have a more or less statistically uniform distribution. This means that the distances between neighboring particle centers were fairly constant before the deformation, which is called the center to center method, based on which the Fry method is developed. The particles could represent sand grains in well-sorted sandstone, pebbles, oolites, pillow lavas, Pahova lava centers, Pluton centers, and any other objects that are of similar size and where the centers are easily definable. This is a very important part. So now, as we can see in this first diagram, if you pick a circular object or particle where you can properly define the center point, and from the center point we can get the distances from the centers of the other circular particles around it. This is before any strain is applied, meaning there is an undeformed state. After deformation we get the deformed state, and this is the final result. So this deformed section has a maximum distance and a minimum, which is defined by the Dmax and Dmin values. So the ellipticity of the strain ellipses are R is equals to the maximum and the minimum. So now let's see how this Fry method is done. It can be done manually by placing a tracing paper with the origin and a pair of reference axes onto an image of the section. So this is the image containing all the particles, for which the center of the particles are marked, and this is the tracing paper over it with the origin and a pair of reference axes. So what we first do is, after marking all the centers of the particles on the initial image, we place the origin of the tracing paper onto a specific particle center like this, which is the one, and then with respect to this particle center we mark all other center of all other particles present in the section. So then the tracing paper is moved without rotating the paper with respect to the section, so that the origin covers a second particle, which is particle 2, this center, and then with respect to this center, as we can see here, now section in the section the particle 2 is of main focus, and with respect to that all other centers of all other particles present are marked in this red dot. So these blue dots were the first centers with respect to this particle when the origin of the tracing paper was placed on this. Then The origin of the tracing paper is placed on this particle 2 and all other centers are marked in red marks. This process is continued till all the particles on this image are marked. So this process is repeated until all areas are covered. So after this, the result will be a visual representation of the strain ellipse as we can see here. The ellipse is the white area in the middle defined by the point clouds around it. So from this strain ellipse, we can get the actual ratio which gives the strain ratio. So now I have discussed the most basic methods of strain analysis like Wellman, Fry, RFI. So now I'll be discussing a bit advanced strain analysis method which is called as the inverse Wheeler method. This method presented here takes the inverse point of view, meaning rather than considering the actual lines of the fabric like this as you can see in this figure and their changes in length and orientation as a function of deformation, what is done is the probability of these fabric lines being intersected on a given traverse which is this is considered. So the proposed method of strain analysis consists of rotating a set of parallel lines like this which are of fixed and constant length through 180-degree and counting the intersection with the lines like this of the deformed fabric at regular intervals of phi, which is mostly 10-degree interval. This figure shows the inverse sulfur wheel at starting position. This is the section, the image of the section that contains all these fabric lines and over which the sulfur wheel is placed. The center of the inverse sulfur wheel is placed on C, which is also the center of all these fabric lines on the image, and then the parallel lines on these wheels are in the direction of X dash. So the number of intersections are counted for each 10-degree interval as the sulfur wheel is rotated, and it is displayed in this graph like this. It is assumed that the number of intersections per orientation, like for each 10-degree, the number of intersections should average 50 or more. As you can see, it is mostly near that in this graph. So, like this, in this x-axis, we plot the intervals, the orientation. See from 0 to here it will be 180-degree, and here it is marked all 10-degree intervals. And in y-axis, we have number of intersections per orientation. So, for each 10-degree interval, for this specific orientation, we have this number of intersections. Now, for another 10, we have this. Now, for this, we have this, and so on. So, now a curve is fitted through these points by calculating a best fit curve. So, after we get this plot, what is considered is the minimum and the maximum values, which is this, the minimum values meaning the minimum number of intersections and the maximum number of intersections is considered, and the angle, the minimum angle at which we get the minimum number of intersections. So then we get is this formula where this ratio of the minimum number of intersections and the maximum number of intersections gives the ratio of the principal axis of the strain ellipse. So now from this principal ratio of the principal axis of the strain ellipse, we can get this, the strain ratio. So these are all this method which is very crucial to understand the strain of a rock. So in a conclusion, we can say the strain is mainly revealed by deformation structures or by means of pre-existing markers that have changed shape during deformation. The strain markers in deformed rock reveals how much the rock has been strained and also subsequently giving information regarding the nature of the deformation. If the fabric is randomly oriented, and then is deformed. Then the resulting preferred orientation of the surfaces carry all the information necessary to derive the finite strain ellipsoid or the ellipses. And the undeformed straight, the 2D section displays lines of random orientation, and after deformation it shows a preferred orientation. So these are the several techniques that I've discussed, and there exist different computer codes that can help us to extract the strain from this deformed drop. Thank you everyone.